Hi, my name is Rodrigo Castellanos. I'm a postdoctoral researcher working at NC State University with Professor Robert Heath, and today I'll be discussing my work on a circuit-based model for multi-polarized MIMO systems. To begin, we'll discuss the motivation for this work, and that really starts from the point of view of MIMO. So MIMO was first conceptualized as a way to leverage multiple antennas at the transmitter and the receiver to spatially multiplex signals and make better use of the bandwidth that was available in those systems. And as the years went on, the reach of MIMO has expanded beyond that initial problem to encompass a large number of different applications and different associated signal processing problems. For example, in the millimeter wave regime, where we had a large number of antennas at both sides of the link, a key challenge was figuring out how to account for practical beamforming architectures where the digital and the analog signal processing was separated, while still being able to exploit the higher bandwidths that were available in that regime. For massive MIMO, we had a large number of users in a network, and we wanted to understand how to leverage the massive numbers of antennas available at the base station in order to better share resources between the many users. And as we move from 5G into 6G, a key question is what is next for MIMO in terms of the applications that we'll see for MIMO as well as the associated signal processing problems. To answer that question, we look at a few emerging applications that we might see in 6G. And these include, for example, terahertz communication, which encompasses the frequencies between 100 gigahertz and about 10 terahertz. And the key challenge there will be figuring out what architectures are able to provide power-efficient communication while still leveraging those enormous bandwidths. For nanoscale and chip-to-chip communication, we'll have devices that are in close proximity to each other. And a key challenge might be how to incorporate mutual coupling between the two nodes of the system, as well as formulating near-field communication protocols. For joint communication and sensing, we'll have to look at repurposing the transmit signal to provide a dual functionality, right, so that it can both transmit information to the receiver, but also gain some information about the environment simultaneously. And finally, we might see extremely large arrays deployed in various networks, right? And these would, for example, be contiguous surfaces of antennas that are attached to the sides of buildings as a way to either reflect signals passively or maybe to actively participate in the communication. And with all of these applications, these might require new and modern antenna technologies to facilitate the implementation. For example, for higher frequency bands and for applications where small form factors are priority, we might have to look at plasmonic antennas rather than electronic antennas, right? And plasmonic antennas are a new technology that enables arrays to be spaced at smaller than half wavelength without inducing significant coupling. In situations where we need a very large array gain or a large spatial resolution, we might have to look at holographic antennas or extremely large apertures, again, to implement those very large surfaces that are composed of a massive number of antennas. And the portion that we'll focus on here today is the use of reconfigurable antennas as a way to enhance the transmission capabilities of MIMO. And we'll go into more detail about what these antennas are and how they will enhance transmission. So as a brief description of a reconfigurable antenna, these are devices that are able to reconfigure their main properties either through an electronic implementation, where you maybe have a diode to switch between a finite number of states, or, for example, a metamaterial implementation, where you have a biasing voltage that is able to directly affect the characteristics of the antenna in a more precise way. And the properties that are able to be reconfigured in these antennas generally include the gain pattern, the polarization, the operating frequency, and even the bandwidth. And the key question we want to answer in this work is how can we leverage reconfigurable antennas to increase spectral efficiency in a MIMO system? And to do that, we'll focus on polarization reconfigurable antennas and look at how those can be used as a way to increase the degrees of freedom in the system. Now, there's been a variety of works that have looked at reconfigurable antennas in the context of MIMO, but there have been issues with these in the sense that they have either focused exclusively on experimental results or they have idealized the performance of the antennas. With experimental results, we get a clear picture of what the pattern and the polarization and really the properties of the antennas will look like, but it's harder to gain analytical insights into the system design using those experimental-based approaches. And with the ideal and the antenna performance, where maybe you idealize the gain pattern or how reconfigurability works, we lose out on the connection between those results and what the practical implementation of that system would look like. And so really we want to combine both of these approaches and develop a physically consistent antenna model that can lead to analytical insights that are still practically relevant in deployment. So to describe the system model that we looked at in this work, we looked at a narrowband single user MIMO system with perfect synchronization. And that really leads to a fairly standard signal model that we've seen before, where you have the received signal that's a function of the combiner at the receiver, the precoder at the transmitter, and the channel matrix that dictates the propagation between the two sides of the link. And the key here in this work is that the reconfigurability will be accounted for within the channel. Right? So we'll assume that the channel model will account for the antenna characteristics, depolarization, relative rotation, as well as over-the-air propagation effects. And so we want to discuss how reconfiguration affects the channel and then see if we can come up with a way to facilitate reconfiguration. So we first discussed the polarization of an antenna. And to give a brief description of polarization, this really is a description of the orientation of the electric field radiated by an antenna. And in practical scenarios, real antennas are not perfectly polarized in a single mode. Generally, you have what is called the co-polarization gain pattern. That would be the direction, or sorry, the co-polarization direction would be the intended polarization of the antenna, right? That could be horizontal, vertical, or maybe a slant polarization. But real antennas always have some sort of leakage into the orthogonal polarization, which is denoted as the cross-polarization gain pattern. And so to fully describe the pattern of an antenna, we need both of these patterns, the copolarization and the cross-polarization, to describe those two orthogonal fields. Now, as we discussed, the copolarization is relative to what the intended direction of polarization is, so it can be useful to have a fixed frame of reference. And here we'll denote those as horizontal and vertical for the antenna array. And we can actually decompose the copolarization and the cross-polarization patterns into their horizontal and vertical components through a simple transformation through a rotation matrix. And here the rotation matrix is determined by a single angle, which we'll call here the polarization angle. And that just denotes the angle between the horizontal direction and the copolarization direction for that antenna. And that greatly simplifies the model that we'll use for polarization reconfiguration, and that will assume that we can change the polarization angle of each antenna. Right? So that angle theta c will be assumed to be reconfigurable. Now, generally, this angle would lie in some sort of feasible set that would account for maybe there only being a finite set of polarizations that are available. Maybe those include horizontal, vertical, and maybe some slants. Here we'll assume a continuous reconfiguration in the sense that we'll have all of the angles from 0 to 2 pi available to us. That could possibly be realizable through a metasurface implementation, again, because those provide a more finite control, or sorry, precise control over their polarization. Right, so apart from antenna polarization, we also have channel depolarization in the system, right? And that's because scatterers modify the polarization of the incident wave and also the power of each of those fields depending on the polarization. So here we'll model channel depolarization via a depolarization matrix, which contains the correlation between the horizontal and the vertical components. But here the key is just to note that channel depolarization is a separate effect from antenna polarization, but it still needs to be accounted for in the system, right? And though here we'll use a simple model with random phases and single scattering cross-polarization imbalance, you could easily implement a more advanced model without significantly changing the findings in this work. Okay, so for the channel model, we used a double directional channel model where the channel is composed of a sum of paths, and each path is determined by 5 variables here. Those include the convex path gain, the rotation matrix for orientation, the depolarization matrix, and then this new quantity here, which we're denoting as the steering matrix. And it is a matrix rather than the traditional steering vector, because we have 2 columns in the matrix, each for those horizontal and vertical components in the polarization. Okay, so when we reconfigure the antenna polarization, we are adapting the steering matrix and therefore changing the channel response. Now, one issue with the prior representation is that it complicates how the polarization angle actually affects the channel. But through some manipulations, we can actually show that the channel can be written as this effective channel here, H tilde, as you can see at the bottom here. And then the polarization reconfiguration can be fully accounted for with these combining and transmit polarization matrices, which we denote here as P. Okay, so we can view the effect of adapting the polarization angles as additional and pre-coding matrices acting on the system. Okay, we know here that mutual coupling between the antennas can affect the channel model, but we can easily account for this using the scattering matrix that could potentially depend on the polarization configuration. Okay, so now we'll briefly discuss the polarization angle optimization. So in this work, we looked at how to maximize the spectral efficiency as a function of the polarization angle. Right, to do that, we simplified the problem by assuming perfect combining and perfect precoding just to fully isolate the polarization angle optimization at the transmitter. And through some manipulations and the use of Jensen's inequality to approximate the objective function, we arrive at our true objective at the bottom here, which is maximizing the channel gain as a function of the polarization angle. And when we do that, we reach a relatively straightforward solution simply by writing the different components of the channel norm here and noting that there's actually a closed form solution for the polarization angle at each antenna that maximizes the channel norm. And these angles will depend on the antenna and the channel parameters, but they can be found in closed form through this expression here. Right, and when we do that, we show here some brief preliminary results for this algorithm where we optimize the channel polarization, right? Those are the dashed curves, and when we keep them static, then that would be the black solid curve. And here we've listed the different parameters. We have a copole power of the square root of 0.8, a copole pattern power of 0.8 and a cross-pole power pattern of 0.2. And we list the depolarization, the number of antennas, the number of paths, etc. And here we note that reconfiguration, even only at the transmitter, increases the spectral efficiency of the system simply by allowing more degrees of freedom to adapt the propagation environment. Okay, so as a conclusion to this work, we've noted that new antenna technologies will enable new applications for the next generation of wireless communication. Realistic physical models of antennas must be leveraged to better understand electromagnetic propagation, and polarization configuration can be leveraged to provide improved performance in MIMO systems, as we demonstrated.